The next learning objective is all about Coulomb's law. So we're going to take a break from gravity and instead focus on electrical charge. That's what Coulomb's law essentially is. Coulomb's law is about the force that two charged particles experience. So the learning objective states that I can apply Coulomb's law on two or more charged particles. So we're going to apply a law, and for this is going to be very similar to when we applied Newton's law of universal gravitation, had an equation and solved for something in it. We're going to do the same thing. And for two or more charged particles, so we could have actually potentially 3 or 4, so on, amount of charged particles. Let's first talk about what is Coulomb's law. So mathematically, Coulomb's law can be seen right here. The force that an particle experiences, a charged particle experiences, is equal to this Ke constant times the absolute value of Q1, Q2 divided by r squared. Before we go on to explain anything else about this, let's just take a look at this equation and realize that should look very similar to another equation that we've dealt with. In fact, there's a funny meme here where we got Coulomb, the person who, of course, created Coulomb's law, and Newton, and Coulomb is looking over Newton's shoulder at his equation for universal law of gravitation, and, of course, cheating from it. Going over the pieces of Coulomb's law, what we have here is a constant. So this constant right here has a value of 8.99 times 10 to the 9th newtons times meter squared divided by coulombs squared. So that's a capital C, coulombs. It's a unit of charge, of course, named after Coulomb. Q1 is the electrical charge of one object, and Q2 is the electrical charge of a second object. Now, just to mention, coulombs are rather big units. For example, the charge of an electron is something like times 10 to the negative 19th coulombs. Incredibly small. But remember, electrons are numerous. If you remember anything from your chemistry days, if you talk about the mole, a typical object that you can see or feel has close to a mole at least of particles in it. And so if you could see or feel something, you can observe something, it has lots and lots and lots of particles on there. So we're talking about tons and tons and tons, billions upon billions of electrons. So if they all add their little charge together, you can get a serious effect. And of course, the R is the same as in the Newton's law of universal gravitation. It's the distance between two charged particles or more. Let's take a look at a specific case. So on the right here, we have a setup where we have two different setups actually. We have two positively charged particles. Gravity always worked where the forces were towards or an attractive force. The force was between the two objects and they were towards the other object. Coulomb's law, an electrostatic force, can be either an attractive or repulsive force. And what depends is the charge. We can have a positive and negative charge. We couldn't have that with mass. Notice the position here of the charges is that looks just like the masses from Newton's law of universal gravitation. So Newton's law of universal gravitation couldn't have negative charges because it couldn't have negative masses. But for Coulomb's law, you can have negative charges. So if they're both positive charges, this force is going to be repelling away from each other. Now what we're going to do is we're going to treat this as the absolute value of the two particles' charges multiplied together, and then we're just going to a fixed direction later. We will use the rule that if you have two charged particles and they're the same charge, so positive and positive, then the force is going to be repelling. If you have two charged particles and one is positive and one is negative, then the force is going to be attracting. You could just think of opposites attract. North and south pole of a magnet attract each other. Two north poles repel each other. The actual statement for Coulomb's law is Coulomb's law states that the electrostatic force, that's what we're solving for the force here, between two charged particles is directly proportional to the product of the magnitudes of their charges and inversely proportional to the square of the distance between them. This force is attractive if the charged particles are opposite signs and repulsive if they are of the same sign. Let's take a look at an application. We're going to go back to our days of chemistry to look at this application. So we're going to ask the question, what is the electrostatic force, so the force that two charged particles feel, because they have a charge, between a sodium ion and a chloride ion? Remember, back in chemistry, a sodium ion is a sodium atom that lost an electron, and a chloride ion is a chlorine that gained an electron. So sodium is the cation, and chlorine or chloride is the anion. To do this, we need to have a couple of figures. We need to know what the charge of each of the particles are, and we need to know what the K value is, which we already have seen in the notes, and we need to know how far apart these two charged particles are. And it's going to be from the center of their masses that we're going to calculate this. This is the situation drawn out. We have in red, so I've color-coded everything. Red is specifically for the sodium ion, and green is for the chloride ion. The red sodium ion has a smaller radius, a radius of 116 picometers, and picometers are an incredibly small amount of meters. And that makes sense because it's an atom, and atoms are incredibly small. And we have the chloride ion, which has 167 picometers as a radius. Now, neither of these numbers are actually the number that we're going to plug into Coulomb's law at the bottom. Both of these numbers are going to be combined together to get us the amount that we're going to put into Coulomb's law, because the distance between is the combination of their two radii. That is the value of R. So if we add those two numbers together, we get 283 picometers. So we have the distance, we have the K value, but what we need now is the charge. Each of these only differ by either having one more proton or one more electron. So each of these ions just have a positive one or a negative one charge in terms of how many electrons or protons they have. So each of these will have the charge of essentially one electron, because electrons and protons actually have the same amount of charge in coulombs. So it turns out the charge of an electron is 1.6 times 10 to the negative 19th coulombs. So both of them have 1.6 times 10 to the negative 19th coulombs. However, the chlorine is negative and the sodium one is positive. Plugging that all into our equation here, what we get is we take that K value and multiply it by 1.6 times 10 to the negative 19th coulombs times negative 1.6 times 10 to the negative 19th coulombs. Take the absolute value of that, and then divide it by the square of the distance between them, which is 283 times 10 to the negative 12th meters, because that is what a picometer is. It's times 10 to the negative 12th meters, incredibly small. Plugging in our calculator, we get an answer of 2.87 times 10 to the negative 9th newtons. That's a very, very small amount of newtons, but remember, this is between two atoms, between two ions. And there are billion of these atoms, these ions, in a sample of sodium chloride that you could visibly see. So the force in aggregate, meaning adding them all up, the force can actually be quite monumental. So I leave you with 3 practice problems. All of these are about using Coulomb's law to solve for one of the variables. So on the first one, you have 2 point charges, so that basically means you can ignore the size of them. You can ignore their volume, just treat them like they're points. And it gives you the values for the charges. Now this symbol right here is called mu, and it stands for micro, and micro is times 10 to the negative 6th. So one of them has 3 times 10 to the negative 6, and one of them has negative 2 times 10 to the negative 6 coulombs. And they're separated by a distance of 0.5 meters, so half a meter. You're going to calculate the magnitude of the electrostatic force between them. And of course, you're going to be using the value of K, that is the 8.99 times 10 to the 9th newtons times meters squared divided by coulombs squared. The next one is similar. You have a charge of 5 microcoulombs is placed 2.2 meters away from a charge of 7 microcoulombs, and then you're going to determine the force between the charges. And then lastly, the last one, you're going to do something different. You're going to get 2 charges, and of course, you're going to get their charges, the magnitude of their charges. And then you're going to notice that we're not asking for the force because you're given the force. You're given the force between them, and you're needed to find the distance between the 2 charges. So you're solving for R in the last one.